So here is an important concept in set theory. It's called cardinality. Cardinality is simply the number of unique elements, in other words, distinct elements of a set. So the cardinality is also called the cardinal number. The cardinality or cardinal number of A is the number of distinct elements in the set A. People often would write this as N of A. But in set theory, people could also write it as A within two vertical bars. Now, mind you, that only applies to cardinality when we are in set theory. Outside of set theory, that notation would mean something different. It would refer to an absolute value. But in set theory, it refers to cardinality. So N of C is 0 because C is just a null set. It has nothing in it. The key word here is distinct. So I could have repeating elements in the set, but that would not be part of the cardinality. For instance, what is the cardinality of B if B is the set 2, 2, 2, 11, 11, 7, oops, 7, 17, 17, 18. So common mistake is to write the cardinality as 1, 2, 3, 4, 5, 6, 7, 8, because there are 8 elements in the set, but that is incorrect. The reason being, cardinality or cardinal number refers to the number of distinct elements. So we have to count the distinct elements. So N of B is actually 4. So we have 2, 11, 17, and 18. Those are the unique elements in B, or distinct elements in B, and that would represent the cardinality. Now, when do we say if a set is equivalent? Two sets are said to be equivalent if they have the same cardinality. So the number of distinct elements in A is equal to the number of distinct elements in B. Now, what you have to keep in mind is we're not saying that the elements of the set A match the elements of the set B. In other words, if I say A is the set 1, 2, 3, I'd require B to be, say, 3, 1, 2. They contain the same element. That's not what we are suggesting. Rather, we are suggesting that they must have the same cardinality. Sure, in the case that I pointed out, the sets are the same. If I asked you, are they equivalent? They certainly are, because the number of distinct elements in A is the same, and it's the same for the set B. So they are equivalent sets. By all means, they are the same set written in a different order. So if I have a set A to be -1, 0, 1, and B 1, 1, 2, 3, 3, are A and B equivalent? So if the cardinality of set A is equal to the cardinality of set B, then the sets are equivalent. Well, what is the cardinality of A? The cardinality of A is 3. Set A has 3 unique elements, -1, 0, and 1. Set B also has 3 unique elements, 1, 2, and 3. Mind you, we're not counting the number of elements, we're looking at the unique elements in the set. So n of A is equal to n of B. Since n of A is equal to n of B, A and B are equivalent sets. Here is another important concept. So what is one-to-one correspondence? Well, if I pick an element A, there is a match for that element B. It could be any element, but there is a corresponding match, exactly one of them. So for example, in the previous case, I had A to be -1, 0, and 1, B as 1, 1, 2, and 3, 3. It doesn't matter how you map them, but I have 3 unique elements. So I can map -1 to 1, map 2 to 0, map the 3s to 1. So the element 3 in set B corresponds to element 1 in set A. Element 2 in set B corresponds to element 0 in set A. Element 1 in set B corresponds to element -1 in set A. So definitely there is one-to-one correspondence. Now, if there is one-to-one correspondence, then they have to be equivalent, period. Intuitively, this is true. If I said for every pet that I have in my house, there is a match in my neighbor's house, then if I have 2 cats, my neighbor either has 2 cats, a cat and a dog, a cat and a rabbit, but definitely 2 unique elements there. So if I can establish one-to-one correspondence, then the sets have to be equivalent. If I cannot establish one-to-one correspondence, then they can't be equivalent. Let's just say, I'll use the same example. Say set A is a cat and a dog. Set B, a cat, a dog, bunny, another bunny, snake, and a cockatoo. So the cardinality of A is 2, cardinality of B, 5. Clearly, the cardinalities are not the same, so A and B are not equivalent. Well, that seems obvious, but let's see if that second statement is true. Do you see a one-to-one correspondence between A and B? Well, if I take the element cat in A, I can associate that with just cat, or dog, or bunny, or snake. So one element in set can have multiple elements in the other set. So you can't establish one-to-one correspondence in either direction. So one-to-one would mean that. In either direction, you simply have one connection. That's all. So if you can't establish one-to-one correspondence, then you don't have equivalent sets. Now we move on to the concept of a finite set. A finite set is one that is countable in some way. In other words, you can write its cardinality. So Well, a set whose cardinality is a natural number would mean the cardinality could either be 1, 2, 3, 4, 5, etc. Well, they're all countable numbers. So if you can count the number of elements in a set, then we have a finite set. Is the null set a finite set? A finite set. A finite set has no elements. If it doesn't have anything, then the cardinality of that finite set is 0. Well, 0 is a valid number. It's not a natural number, but it's a valid number. So we have to realize that since 0 is not a natural number, we have to sort of insert a condition. The condition being, or the cardinality is 0. In other words, it is an empty set. Either we want it to be a natural number, or it is 0. You may, again, if the cardinality is 0, if I say there is nothing, I'm able to say nothing because I'm able to count it. So if I can count it, there is some finite nature to it. So the definition of a finite set is that the set must have a cardinality that's a natural number, or it's just 0. There is only one set which is going to have a cardinality of 0, which is a null set. An infinite set, naturally, an infinite set is simply a set that is not finite. That's it. Now, is the set of natural numbers n an infinite set? So n is an infinite set because it is 1, 2, 3, 4, ... It keeps on going. Anytime we throw an ellipsis, it means it keeps on going. There's no end to it, which means you can't put a finite count to it. So it is an infinite set. So equality of sets two sets are equal if they contain the same elements regardless of order or repetition. So A, 1, 2, 3, oops, and the set B, 3, 1, 2, from earlier when we talked about equivalence. Right here, I mentioned, well, sure, the two sets are equal, but are they equivalent? They are completely different things. Equivalent sets have the same cardinality. Equal sets have the same elements, regardless of repetition or the order in which you write set A 1 to 3, set B 3 1 2, set C 1 1 2 2 3 3 5. I want to know if A and C are equal, if B and C are equal. No. Because the set C has one additional element that is not in set